Thank you, and hello everyone. I, as many of the crew team, also had a busy week last week at KubeCon in the US. I hope my voice is fine. I hope I don't fall asleep while I'm up here because of jet lag and everything. So let's see how this goes. Thanks for having me. As introduced, my name is Mikkel. I work for a company called Fermyon. Fermyon is a company that is 3 years old, was founded by an engineering team who's done a lot of open source projects in the Kubernetes space, projects like Helm, Brigade, some of those that they founded, and now moved on to WebAssembly, which is interesting. I was actually thinking about the keynote that Mark gave about, are we making progress? I was sitting there having a little bit of doubts of whether this thing is progress or not. I'll leave it up to you whether you think WebAssembly is progress in terms of where we are today. I'm actually pretty sure it is, and I hope that I can tell you a very compelling story of why I believe that WebAssembly is progress in terms of how we think about creating systems, how we think about creating platforms, what platforms even are, and how we make it easier for developers, and how we make it much more efficient what we do. So, let's talk about WebAssembly and WebAssembly component model. Two questions. How many in here do not run containers today? Everyone runs containers. Okay, does anyone run WebAssembly? Few, small hands, 3, 4 hands. Okay, cool. That was sort of also my expectation that we're at the point right now where everyone runs containers. Very few do WebAssembly, but everyone at least runs containers. And we at Fermyon have talked about WebAssembly as sort of being, we believe, is the next wave of cloud computing. So thinking about physical servers moving into virtual servers, moving into containers, trying to create these smaller and smaller, more agile building blocks for our systems. And it's not, I don't think it's a reasonable assumption to have that WebAssembly becomes that new core primitive of how we build systems. So what is WebAssembly? What's the problem? And what are they trying to solve? Originally, WebAssembly was created to expand the programming languages that we could support inside of a browser, so on the web. So a lot of you have seen examples of people running old Doom games inside of the browser, meaning they've taken some of these games, probably written in C, C++, something like that, compiled them to WebAssembly, and then are able to run them inside of the browser. A lot of this comes from sort of the evolution of the Flash and the Silverlights and those type of plugins that were created for the browser that were all proprietary technologies. So this was really a way of trying to create an open standard, which means that at the core of WebAssembly as a specification is a specification to have these safe and very portable low-level code format with efficient execution and compact representation. So, strong isolation, runs anywhere, are quick, and are very small. Now, if we think about those 4 things as being things that we could think of as good things to have, when we build our platforms, we run our applications in general, maybe compared with containers, which have less isolation, needs to be built against specific operating systems and processing architectures. Can take some time to start up because you often put a lot of processes as you start your containers and are not necessarily that small in size. There are some promising signs in here just from the very core of what WebAssembly is. So if we sort of take that as a where WebAssembly came from, so this thing we run inside of the browser, I've created this sort of unofficial and very rough timeline of these events. So we had this new compilation target for the browser, which means we can use a variety of programming languages, compile to bytecode format, run things in the browser. We call those WASM or WebAssembly. They are built on these things called WebAssembly modules. Then somewhere in the middle, someone had this idea that maybe we could make this thing useful outside of the browser as well. So again, taking those 4 core capabilities and say, what if we ran this outside of the browser? This is where WebAssembly System Interface, or WASI, came into the picture. So WASI is basically an API specification that you could say could be considered an operating system. Something that you as a developer, when you develop something, this is the set of low-level APIs you have. So what can I do in here? And then where we are today, are sort of at the very front of what is happening, we've talked about how we can make these things composable. So small components that, again, are isolated, efficient in terms of size and how quickly start. And part of it is coming up with a specification called the WebAssembly interface type system, which we'll talk about as well. And this is where we sort of introduce this whole component thing. So think of this as WebAssembly came from the browser to solve some certain problems there. We figured out we can run them outside, so we gave them access to things like files and standard I/O. And now we have this idea of creating or composing applications out of making these bits and smaller and have defined interface between them. Okay, so let's start with somewhere in the middle and say, let's try and figure out what this WebAssembly system interface is. So as I said, the goal with WAS is to find this API so that a WebAssembly can interact with things outside of its own little world. So when you run a WebAssembly inside of a WebAssembly runtime today, you have this linear memory profile, which means that the WebAssembly itself only has access to its own set of memory. So the only way that a WebAssembly can talk to something outside would be via a set of APIs that would be provided by that runtime or by the host, and this is basically what WASI is. And again, you can consider this to be somewhat similar to an operating system, but it's less, you have a less wide surface, API surface, than you would find in an operating system. So it's also not a full operating system. And some of you may then realize that there are definitely compatibility issues in terms of what you do today and how you write code today, in terms of what APIs you expect and what you will find inside of WASI. But what WASI at least defines sort of as the first use cases that have been tackled is how can we create a command line interface, so CLIs, so things where we can run stuff. We have standard in, standard out, standard error, those things. And how can we deal with HTTP requests? So building things that respond to HTTP requests. And how can we then get access to things like sockets, I/O, random numbers, clock, and file systems, which are the core pieces of what this specification gives us. So the two use cases that WASI 02, which is the current version of the standard, supports, as I mentioned, CLI and HTTP. So what you see here is actually a representation of what that is. And so I think the main thing to take away from this is that there are these sort of standardized exports, means that if you build a WebAssembly component, you can either export a function called run, which means I can call you from a CLI, or you can export an incoming HTTP handler, which means I can call you through an HTTP request. So you kind of hopefully start to see this idea that you have a very defined set of ways of interacting with WebAssembly components sort of from the outside in, but also how these components get to access to things from the outside. So you can see in both these scenarios, you have a list of imports, which are functionality that are being provided to your component. So for instance, on the HTTP side, you can see we have this WASI HTTP outgoing handler, which means that our HTTP WebAssembly now actually have access to also send HTTP requests out. And on the CLI side of things, you can see we would have things in environments, so getting environment variables, and we have terminal input and output, and so on and so forth. So if you want to build some of these, or sort of the tech stack that's needed to create this, first of all, we need a compliant runtime with WASI 02. WASM time is the runtime that is being built by something called the Bytecode Alliance. Very rough shapes. Think about the Bytecode Alliance as the CNCF of WebAssembly. It's not quite what it is, but it is an alliance between a lot of companies who are trying to build a lot of tooling around WebAssembly. And then we need a programming language that can compile to WASM or WASI. And we have compiled this language support matrix that gives you a really good overview of sort of the state of support in the various programming languages that exist today. So what this means is that if I want to build a WebAssembly in a given programming language, I'm showing .NET, TinyGo, and Rust up here, it's basically just a compile target. That's how they sort of all trying to tackle these things. So if I build Rust code, I compile against the WASM32 WASI target. If I use .NET, my runtime identifier would be WASI WASM. If I use TinyGo or Go, I'll basically have a target called WASI or something similar like that, right? So that's how my code gets into a WebAssembly. Let's do a demo and just see how such a WASM module would actually look like, where we try to implement one of these WASI CLIs and we use the WASI files interface. And it's a fairly straightforward demo that I'm going to do here for now. I actually already wrote all the code, so we don't have to write it, but at least we get to look at it. Okay, I'm using Rust in this case, and it's really just to give you an idea of how how simple these things can be. In Rust, I've implemented a main function. Other programming language, like just, this is what eventually when someone, the run function that is being exported, that is defined in the CLI interface, this is how it's interpreted at. So basically, I'm gonna create a string where I am reading a file from this hello.txt, and if I don't get that, we'll throw an arrow. If we're actually able to read what's in that file, we'll print that out to the console. Okay, so what I would do in this case is I will do cargo build, and I'll target wasm32 WASI. So now I'm in that world of building these WebAssembly. I did already build it, which is why this ran so fast. And then I will use my, actually let me just go up here. Then I will use my WebAssembly runtime, so wasm time. And I can go and run this WebAssembly that we output, and we will see that things are blowing up immediately. And that's because I want to show you one of these things that WebAssembly have in terms of isolation and security. In these WebAssembly runtimes, there is a security model called capability-based security that's been implemented, meaning that at runtime, we as an operator, we get to specify the level of access this WebAssembly get to that outside world. So even though that we know that we actually, in our wasm time, we did provide access to the file system. As we ran this, we didn't provide the access at runtime. So you can see our exception message came out, and we can probably see in here somewhere that, failed to find a pre-opened file descriptor. So basically, our runtime did not provide access to the file system. So what we would do instead, if we want to run this, is we would set, let's load in the current directory, or provide access to the current directory as we run this, and now we get access to read the file and output that. Okay, so that's a very basic, scenario of using WebAssembly. What's good about the WebAssembly thing that I have up here is that, first of all, we just saw the capability-based security model with runtime-based sort of definitions of what we can do and whatnot. But the same wasm can actually run on, I built this on a MacBook up here, but I can run this across any processor where the wasm time runtime runs, and any operating system. I don't need to build additional, I don't need to create additional build artifacts out of this. And another thing we could look at is, just very briefly take a look at the size of this. I think, well, this is a release build. So we're talking about around 90 kilobytes for this particular WebAssembly, and we can actually strip that down even further by removing a lot of information in the wasm file if we wanted to. So that's it. We have a fully functional CNI that we can run here. Okay, so what we did here is we used that runtime underneath. We have the set of WASI APIs that's defined, and we were implementing WASI CLI, and we were using WASI files. Like, the whole tooling we have here did not show that, like, we weren't as developers exposed to this, right? But that is what is going on behind the scenes, and this is sort of where this thing started. And I'm trying to take you to a progression of where we can see we actually get to have opinions about these interfaces and define new interfaces as we move along. So what if you wanted to do something more compelling than just CLI? Well, we came up with this framework called Spin. It's an open source framework. And what we've done is we've really taken all of these concepts of WebAssembly and component models, and we built a serverless framework. And by serverless framework, it's mainly because the programming paradigm model is that you're going to build these WASI HTTP components, which means you're going to implement something that expects an HTTP request and returns an HTTP request. And that's really all you have to be concerned about. You don't have to think about web servers. You don't have to think about all these other things that sort of goes before getting an HTTP request to your code. You only have to be concerned about that particular part. And it's like lambdas, right? It's like Azure Functions. It's like those type of serverless frameworks that you know. But because it's built on WebAssembly, the operational model that we can apply to this sort of down the road after it's been written is much, much more flexible. So let's try and build a Spin application now where we actually use Spin as a developer tool. I'm going to use that, first of all, because I think it's an awesome tool we built, but also because I hope it will sort of start showing you some of these ideas of what you can do with this whole component model thinking. So again, we have our wasm time that we have embedded in Spin. We have the WASI APIs again, but now we're going to implement an HTTP module at the very top to do stuff with HTTP. So let's go over here. We're going to do spin new to create a new application. We can do TypeScript. We have all the programming languages. Well, I think we have all the programming languages supported with WASI. We can run those, but we have these templates for TypeScript and Rust, Python, Go, .NET, JavaScript as well, SIG, other types of languages that you want to apply. There's a whole templating system to this that you can use. I'm going to do -A because I don't want to walk all through all the prompts that the template provides me to. But let's do a KCD TS. So let's go into this. And we're going to run an npm install because we now appear to be a TypeScript developer. So we need our npm packages. So as this is going to install this, the small HTTP that I had up here, so spin new -t really means that I'm choosing a template. And there's a template called HTTP-TS, which is just short for saying that this is something written in TypeScript, and it expects to work with HTTP. The expect to work with, we also call those triggers. So in this whole serverless model, you can think that you could want to monitor a Redis queue, you could think you wanted to listen to MQTT or other things. Those are just triggers in this framework, and you can sort of extend that by building new component interfaces. And we'll get back to that a little bit later, but for now, let's just take a look at what we have in here. So two things to think about that Spin sort of provides for developer experience on top of this. We have this spin.toml file, which is an application manifest. It describes what this application is all about. First 6 lines is a bunch of metadata, and then you can see we start introducing this concept of a trigger. So we have an HTTP trigger in this system, and it's listening to all the routes. This is a wildcard. And whenever an HTTP request hits this endpoint, hand it over to the WebAssembly component called KCD TS. Now that component is specified down here. You can see it is served by a WebAssembly module. And what's interesting at this point is that nothing in here tells us that this thing was written in TypeScript. I was actually just about to say Rust, because it could as well have been Rust. So you sort of get this idea now that at this time when we would run these things, we just have WebAssembly, and we have this application model where we can structure things together. There's a bunch of extra things in here that just makes it easy to do, sort of have a developer experience around this. Whoops. And I can show you in a little bit how that looks, but this is all the code that I have to care about. There's an SDK, and really what this SDK does is just wraps all those WASI interfaces that I mentioned before. And beside that, I export my handler function that takes a request and uses a response builder to return a response, and we can log to the console, and we can say, hello. We probably want to say hello KCD, right? That's what we do. Let's write that, and let's do spin build to build this thing, and then -u to also do spin up, because you spin up a spin application. So once we have that up and running, we should be able to curl. You can see the local endpoint, and there, hello KCD. Okay, so now we have a WebAssembly component that wasn't a run function that we implemented, but this is something that uses HTTP, implements an HTTP handler. And how do we know about this? Well, there is a tool that I want to show you here called Wasm Tools. So the way that these interfaces, let me just, I think I might have this on a slide that will make a little bit of sense. Yeah, so you can think about Spin as not just, giving you the ability to build things that can respond to HTTP requests, but sort of give you more of a comprehensive set of things that we think would be nice if you wanted to build APIs or those kind of HTTP backends that are out there. Meaning that you probably, at some point in time, it would be nice to store things in a key value store if you want to do some kind of caching, you want to have access to relational databases, and maybe you want to do LLM generation, and so on and so forth. Maybe you want to load in configuration and all these other types of things. All of that is actually expressed in this interface definition that is called the WIT. Sorry for the small font here, but this is actually the complete set of interfaces that is provided inside of Spin. And what's quite cute about these is that these are called worlds. So we have a Spin world, and you can create your WebAssembly components to live in the Spin world. But what's even more interesting about this whole component model is that you can build your own worlds. You can start to define the set of worlds that make up the hosting platform that you want to provide developers, so that developers can, at a, let's say, at a sort of fairly high level, but also very scoped, scoped thing, I don't know what, area, dimension, whatever you want to call it, write the business logic. There's actually no one saying that they even should have to deal with something like HTTP requests, but we can get back to that in a bit. So what we can see is that the Spin application we just built, and we can use this Wasm Tools utility to actually go and take a look at what's inside of this WebAssembly we just created. We have it here. Oh, I actually want to, because this is just going to spill out the whole thing. Whoops. What am I doing wrong? Oh, need a space. Okay, let me just, oh, sorry. I need to add a word in here. Jesus Christ. Okay, so let's just take the first 30 lines. So what we see is that what this is outputting for me is what are the interfaces in the WebAssembly component that we just built. And even though we were using the framework as a developer tool, templates and these things, these are fully compliant WebAssembly components that we could go and run in any runtime that would provide all these interfaces that we import here. And you can see all the ones that are called WASI something are part of sort of the standard specification. Then I guess the developer forgot to namespace this one correctly because they were supposed to be called Fermyon Spin and not Spin something else. Anyways, we'll draft the block or bug later. But you can see there are things that we provide in this framework with Redis and Postgres and MySQL and other things that are just defined interfaces of how you would interact with these underlying systems. And this actually gives another, sort of a good opportunity to also talk about how these implementations actually work. If you look at the key value thing up here as an example, because these components have a defined API to talk to key values. So you can get, you can set, you can get all, you can do other things inside of that interface. The host implementation is sort of up to the host. As long as you implement something that implements everything that is in that API, you can either use Redis underneath, you can use Valkey underneath. When you run this locally using Spin, we just use a SQLite file. We built a cloud, Fermyon Cloud, where you can run things, and then we just use DynamoDB. So you have this world where these components, use defined interfaces, but then it's sort of up to the provider of the platform how you want to honor those interfaces or what the implementation you want to use behind all of those. And that's actually pretty cool that you can use these type of things. And all of this is just how this whole component model actually works together. Okay, if I wanted to now move this into Kubernetes, which I assume is something that would be of interest for many of you, we have a plugin. So I think the first thing that you should probably introduce is some of those deployment targets for Spin apps. So SpinCube is that open source Kubernetes project that you may or may not have heard of. We have some other stuff that we built on the far right-hand side. But basically what SpinCube enables, that is just another open source project, is to run WebAssembly sort of in a Kubernetes native way, right? So you have an operator, some runtime that will be installed in your cluster once you do this. And once you have them in there, you can package up your Spin applications in OCI, and you can easily create your deployment artifacts. So let's just quickly do that. I think we will have time to do that. So we use a plugin to Spin called SpinCube. Funny. I don't know who came up with that. But again, Spin has plugins, right? So you can write all these various plugins. We obviously also have a Spin doctor, because you need a Spin doctor sometimes. But SpinCube is what we can do. So we can say, well, let's just scaffold. That's actually not what I want to do to begin with. I want to do something else. I want to go and push this into a registry. That's the thing I want to do. So let's go and push this into a registry. So Spin registry push, package up my WebAssembly, my spin.toml file, if I had any static assets that I needed to bring as well, and push that into an OCI registry. Do you know about TTL.sh? Sort of like it's just an ephemeral public available OCI registry. It's super awesome if you want to do demos, because this image will go away in an hour. That's why I use the 1H as the tag up here, so I don't have to think about things lying around for too long. What I want to just show you very quickly about the thing that I pushed into OCI, we can take a look at inspecting what's inside of that. And that's not the right one, just a sec. Because you will see, Jesus Christ, there you go. You will see that this is not your regular Docker container. It has the JSON config that we need here, so 209 bytes of JSON config. Then we have a WebAssembly. Now this was a JavaScript thing, so it's not quite the Rust size. And there's a whole story to that, and we can talk about that later if anybody wants to talk about that. And then we have our spin.toml file. So those are the only two artifacts that we need to move around. We don't have file layers, file system layers that are tarballs like we do with containers. It's just we only need the WebAssembly, and we need that spin.toml file to sort of tell a spin engine how this whole thing's work. Okay, then let's move on and do the scaffold. Really what we do when we scaffold things is that we just create a YAML file that makes it really easy for us to deploy things. So you can see now we're in the Kubernetes world. We have SpinCubeDev as the API up there. We have this thing called a spin app, so that's a custom resource you go and create in your Kubernetes cluster. And we want to run this image. And all I need to do is simply go and apply that. And I should have a Kubernetes cluster running over here, where hopefully in a few seconds that KCD pod will turn up. What am I looking at right now? We're looking at deployments. Oh yeah, I wanted to give you a quick overview of what happens when you install SpinCube. So we have an operator in here, and we introduce those various new resource types like a spin app and a spin app executor. And basically the operator ensures that everything are being created based on creating a spin app. The idea with having spin app as a particular resource inside of Kubernetes is to sort of mimic what you see in that spin toml file that I showed you, right? There's an app definition. So if you wanted to import runtime configuration and other things, you would specify that in that YAML file. But basically what happens is that we take that and we have what's called a shim in containerd. So this works with the containerd runtime. And that shim is a wrapper around this whole spin engine, spin runtime that you use. So basically, we end up running a single process inside of the C group where we run these. We don't run a whole set of file system things that you would normally do with containers. And you can see we now have these two things deployed in here. And if we do L, you can see we can get logs, and my OpenTelemetry doesn't work. I don't know why, but anyways, at least there are logs that we can see in there. So I hope you get the idea that it's very Kubernetes-ish, the way that this works. Like there's nothing, push stuff to registries, create YAML things, and then off you go. And that's really the whole point in how we try to set this up. Okay, that got us covered with Kubernetes as well. So let's move to the component model and arriving at the now. So all that you've seen with Spin and how this works, and this was the HTTP interface, I mentioned KV, all of this is actually built on what you can do with the component model. So what the component model adds on top of WebAssembly and WASI and all of this is to, have a way where we can have these WASM components that are compiled independently, which means they can come from from different programming language. But at runtime, we can actually compose them together into applications and into, creating sort of a scenario out of distinct functionality. Just think of this as the same as if you're building something inside of a particular framework or anything. You import a bunch of packages and libraries that someone else wrote, and that sort of helps you, deal with a lot of things and a lot of code that you don't have to write. But we get a lot more with the WebAssembly model of doing this. First of all, we get the polyglot thing, which means you can write something in Rust and you can use it from TypeScript. We get memory isolation between these components, so any library that you would import is isolated in memory from what you run, and only have access to the APIs that are specified. And we get like these very small bits and pieces that we can deploy and run. So it provides a richer typescript than what WebAssembly has, and this is really just trying to fix some of the shortcomings of WebAssembly. Then we had this WIT language that I showed before, where you can see how we can define interfaces so we can compose applications. Okay, so last demo, I hope we can have time to do that. Let's actually try and build something again, and I think this is probably even going to be a spin app, actually. So we're going to use WASM HTTP at the bottom. Then we build the first WASM component A, which is our spin application, like the TypeScript thing we just did. But now we're going to take another WASM component that was created, and we're going to use that in our application. And hopefully I can give you an idea of how these tools work together and something we can do with this. So let's start by taking a look at a component I built. So the first thing I did when building this component is I defined a new world. This is the WIT thing, so this is the interface type language you use between WebAssembly. So you can say I have an interface called city info that has a function called give me a current city, returns a string. And what this world called cities does is that it exports the city info function. Okay, so you could say that I've sit down, I created this contract, now I'm going to go and implement this thing. And, oops, that is what I have done in Rust. So first of all, I'm creating a set of bindings. So you have tools to do that, to generate these bindings. And again, it depends on the language you use, how these bindings have been generated. But once these bindings are generated, basically just translating the WIT language into Rust, right? And if it was .NET, translating WIT to .NET, or so on and so forth. So in this case, in Rust, we're implementing a trait called guest for the component, where we basically implement the current city function and saying, current city is Copenhagen. Okay, we'll go and export that interface, and that's all we have to do. I will then do cargo component build. I'm going to target something called wasm32 unknown unknown. I don't know why it's unknown unknown. I think it's because there has to be something, and it's nothing. But really what this does is that it strips away all the WASI stuff, because there's nothing in the component I'm building that uses, anything standard in or standard out, because I'm not even writing an exception message and things like that. What this means is that what comes out of this is a WebAssembly where if we look at the WIT inside of it, this is all there is. Okay? So we don't rely on anything to run this component. We just give a function called current city that you can call from another component. So the next thing I could do is I could actually put the WebAssembly component in an OCI registry, because OCI registries are everywhere. You probably kind of get the sense now of some of the immaturity around this whole ecosystem, in that I'm pulling up yet another CLI tool, this time called WEC, I think. There's also something called WEC, by the way, not to be confused with WEC. But don't bother. All we do is we take this component and we put it in an OCI registry. And for some reason, people had decided that we are going to use a WebAssembly namespace kind of syntax here, which means that if I wanted to go and do a Docker manifest on this one and inspect what actually ended up in that, I'll have to somehow translate this into, this would be Mikkel, and then it would be cities, and then it would be not at, but use that as a tag. And now you can see, again, I just have a WebAssembly in OCI. So this component that carries this interface definition now sits in OCI, and I can start using that. Okay, so let's go back, and hopefully have time to do this. Did I actually already create this? I did. I think I did. Yes, let's do this. We're not going to get to the last one of these. No, this is not the one. No. Okay, now I know what I want to do. Sorry, let me go. Okay, let's create a new spin application. We're going to use Rust this time. Let's see, KCD Rust. Almost KCD Rust. And then we can start doing things like, we're going to add this dependency to our spin application, right? We call that thing in the registry that we just pushed up there. Consider this to do, cargo add or npm install or whatever. I chose which component I want to use this from through my little guide. And then I'm going to generate my bindings. So what comes out here is probably not called spin cities anymore. Let me just check. It is called KC Rust. Wait, almost there. There you go. And what I have now is I have set up bindings to use this. So I could go ahead and in my code, I could import the bindings module. My analyzer is a little bit slow in here. And then I can start using that current city thing that was defined in this other component, cities, and there we are, current city, that's the function we want to import. And then we could actually call that down here. So we could just, for the sake of this, let's just print a line and say, what we're going to do, something like this, and then let's just call it current city. I think this should work. Current city, there you go. Okay, and we can do spin build and spin up. And hopefully you can see that now my HTTP application, this one component, just used that other functionality through an OCI WebAssembly hosted component that I've imported. And there is, oh, I did this 5 times the other day, sorry. Just need to add one package, and then it should work. And we should be able to see that we are currently in Copenhagen. Well, I mean, it's hard-coded, but whatever. That also didn't work. Okay, something didn't work. If you're interested, I'm going to show you some of these. I have some other examples, but I'm really running short of time, so I just want to quickly round this off. So, what I hope that some of the takeaways here is that there is a sort of a useful reality out there today, right? There are standardized worlds for common scenarios. So the CLI was one of those, HTTP was another one, and then you think about key value and runtime configuration. And what we're really trying to establish through the specification is this combined set of interfaces called a WASI Core Cloud. And you can think of that as, we work together with Microsoft on this, for instance, but you could think about this as various platform providers, whether those are public clouds or whether that is on your own Kubernetes using something like SpinCube, that you would have standardized, or you would have ways of implement that core cloud world, which means that if you write these serverless functions, HTTP functions, anywhere where a core cloud compliant world is offered, you would be able to run your serverless functions. So, I mean, in short, portable lambdas, whatever you want to call them, or something like that, but that is kind of the vision of what we're trying to get to with some of these interfaces, is to be able to, at a very high level, describe what's being available for you as a developer in order to host these. So Spin and SpinCube are host implementations for this. Nginx unit has a web server. It's a web server. Can also run WASI HTTP components. Easy way of getting started. Spin, SpinCube, OCI, Kubernetes. We came hopefully through all of these if you want to try some of this out. Thank you. I'll be open for questions and anything afterwards. Thanks so much.